Welcome back once again. Today we are going to talk about a very interesting subject, standing waves. Standing waves are pretty much the basis of almost every musical instrument that we use. And it's an interesting phenomenon that happens. And so let's try to get our heads around how it actually works. First, let's lay down some groundwork. Any wave will reflect back, or will reflect off of, a change in the medium through which it's traveling. So that sounds complicated, but it's not really. What that means is that a wave, if it's vibrating a particular object, then the vibration doesn't really know, or isn't really aware of the fact that that object might come to an end and then become a different object. So for instance, imagine a string. If we set a wave vibrating through this string, it will travel down the string until it reaches the end of the string. The end of the string is like a change in the medium, because once the wave reaches the end of the string, it must now either begin to transmit itself into the air, which it will do to a very small degree. But also, what's interesting is the wave will reflect backwards on itself and bounce backwards through the medium that it was coming in. And so that's the important part that allows us to create the concept of a standing wave. So let's look at how that might happen. This wave goes this way. It hits the end, and it will bounce back. Now, there are two important bounce back rules that you have to learn, and you have to remember. We've talked about a couple of them. This is what would happen to the wave. It would bounce off the end and start coming back this way. But I want you to notice something very important. This wave is leading with a trough, followed by a crest. But when it hits this end of the string, if the end of this string is fixed in place and held tightly, I'll draw a little clamp here, so that it cannot move, then what we get is an inversion, phase inversion. Or what that means is a 180-degree phase shift from the reflection off of this end that's fixed in place. This is called a fixed end. Or sometimes we refer to it as a closed end, as you'll see in different circumstances. So whenever we have an end of a medium that is not free to vibrate, it's fixed or held in place by something. It could be a hand, it could be a clamp, it could be just the nature of the setup. But if it's not free to vibrate, then the wave that comes back will be inverted by 180 degrees. Now the interesting thing is that we have waves that are continuously coming this way, which are now going to be interfered with by the reflected waves coming back. And it's the interference of these reflected waves coming backwards against the incoming waves that can create, in certain circumstances, the standing wave. But before we do that, there's also another possibility. This wave could be moving in like this, and again, we'll notice that it's leading with a trough, followed by a crest, and it's moving in this direction through the medium. And what can happen, or what would happen, if the end of the string was not fixed or was free to flap up and down or vibrate, is that the wave would reflect, but there would not be a phase inversion. So here there is no phase shift. You'll notice on its way back, it is still going this way. It is still leading with trough followed by crest. So it hasn't flipped upside down, so to speak. And this happens when you have a free end. Oops. Okay, and by end, I simply mean the end of the medium, free end, or an open end. And what that means is the kind of interference that we will get will be different in the case of the free or open end than it would have been in the fixed end, because of the way the waves are inverted in one and not in the other. Okay, so that's all kind of a review. Free end, the open end, the fixed end, closed end, and the phase shift or inversion. All right. So let's write a statement that kind of describes a little bit of what we're saying. We've already written this one. We're kind of going to write pictures and statements together. The wave will reflect off of a change in the medium through which it is traveling. So obviously the end of string represents a change in the medium. And it reflects backwards on itself. This is very similar to the way a wave reflects off the surface of water from air, which is a change in medium. Even though it can easily pass through both, there is a reflection that happens because the medium has changed. All right. Certain frequencies will interfere with each other as they reflect in such a way as to create or cause, let's put cause, unique patterns in the vibrating medium. Patterns of vibration. And only certain frequencies, as we'll see later, when we get a little bit further on, we'll understand why only certain frequencies will do this. But for now, we'll just write that statement. So what that means is, let's think about it again. You've got a wave traveling this way, and perhaps we could use a fixed end so that the wave coming back is inverted and traveling this way. And these waves will overlap. Now I'm drawing one wave, but remember, this is a whole string of waves that are coming in this way, and they're all going to be reflecting and going back this way. So you're going to get a huge overlap, and you're going to get, when the waves overlap, an addition of the waves. Now, depending on how that addition works out, you're going to get, places where you're going to have constructive interference and places where you'll have destructive interference. But what happens in between here, of course, depends on how the waves meet. And one of the things that determines how the waves will meet is how long the string is, because that determines when the wave travels down the string and bounces back and starts to bump into the incoming waves, what's bumping? Do we have a crest on a crest, a trough on a trough, a crest on a trough? How is it going to play out? So the length of the medium is a very important factor in determining how these patterns will play out. And in some cases, there won't be any particular pattern at all. You might end up with just some kind of weird, convoluted addition of the waves that might look something like this. It doesn't really have any pattern to it at all. There's no regularity. However, there are certain patterns that do exist. Okay? So, the patterns, these patterns that we're referring to up here, are called standing waves because they appear to stand still. And that's important to remember, they appear to stand still. And we'll do a little demo in class to visualize this. And Maybe I can try to make a video of that demo and post it up here with this video in conjunction with it, so you can see that. Because they, up here, we'll put that in quotation marks, to stand still. And they are not really standing still, because there are waves shooting back and forth through the medium continuously. But the way the waves interfere gives us the illusion that they are standing still. The way they interfere with each other. Okay. So the typical pattern that you get, let's think about it. A wave going this way, a string of waves that are bouncing off the other end and interfering with waves going this way, are going to create these patterns with certain frequencies. And here's a typical example of what the pattern might look like. Very simply put, there's going to be some places where the waves are going to interact constructively and produce large vibrations. And there's going to be places where they interact destructively and produce virtually no vibration. So what tends to happen is the string begins to take on a vibration. All right? And I'm going to draw an axis here right down the middle just so we can visualize what's going on. And then the pattern that you would visually see looks something like this. This wave that I'm drawing in here sort of represents the other position of the medium. So it's important to realize that I didn't draw two different waves that are interfering, because obviously if I did, these waves would interfere and produce nothing, because they're 180 degrees out of phase. What this represents is a rapid flipping back and forth. So if I draw this red wave, the red wave, in a very short time, flips itself upside down. The string vibrates in such a way so that it suddenly becomes the blue position. So what we get here is a region where it's flipping back and forth from red to blue, with a very large amplitude. And again, in here, it will be flipping back and forth. And it creates this illusion of this sort of loopy section of the medium. And here as well. These sections are actually called loops. Loops. But there are also sections where, and of course, the cool thing is if you get just the right frequency, these sections will always stay in the same place. You'll always get the most positive constructive interference that you can get here, creating these large amplitudes that flip-flop back and forth. In between, you will always get areas where the two waves, the reflected waves and the incoming waves, are interfering to produce virtually no vibration. And these are called nodes. And they seem to stay in one place. So nodes are where you have complete destructive interference and no vibration. And we also use another word to describe the loops. Now that you have learned nodes, these are often referred to as antinodes because they're the opposite of the node. An antinode. Okay. So you'll see that there's a pattern. And the pattern is very, very simple. You end up with it's always going to be a repeating unit of an antinode, followed by a node, followed by an antinode, followed by a node, antinode, node, antinode. You'll never see two nodes together or two antinodes together. The trick is that the starting position and the ending position can be different depending on whether or not the end of your string is fixed or open. If you have an end that's open, an open end will always be free to vibrate. So it has to be an antinode. Open or free end will always be an antinode. Because nothing's holding it down, it's going to flip-flop up and down very vigorously. But a closed end, or a fixed end, will always be a node. So you can see that the length of the string will determine the frequencies that work. but we also have to consider whether the ends of the medium are clamped down and fixed or free to vibrate. That will also determine the frequencies that will work for a scanning wave. So you can start with a node or an antinode, but then you will always follow a progression of alternating one or the other until you get to the end, and you would always end on either a node or an antinode, depending on what kind of end you have, open or closed. So all that's left for us to do is to explore the possible patterns. So let's begin with a simple object. Now remember, because we have to deal with different situations where we have open or closed ends, we have to do a couple of different examples to show the differences between them. So let's begin with, I think, what might be considered the simpler version. And this is fixed at both ends. So this is example 1, I guess you could call it, or case 1. If we have an object that's fixed at both ends, let's use a string. Okay? It's easy to draw a string and it's easy to visualize. So the simplest pattern that you could get, if I'm fixed at both ends, that means one end here of my string must be a node. If it's a fixed end, it can't vibrate. And of course the other end must be a node because it can't vibrate. Well, the simplest pattern then, the simplest situation would be to have one antinode in the middle. Let me draw that a little lower. To put one antinode in the middle, node, antinode, node follows the rules. What would that look like? Well, it would look like a wave form that was vibrating. It would look like basically one loop. And we would see the string flopping up and down, kind of like the side view of a skipping rope. If you ignore the rounding motion and just the up and down motion you look at, we would see this loop. We would notice it has one loop. I'm going to put a little L here to show us that this is the length of the string involved. And the string is flopping up and down, vibrating in this simple way. Now, if you look at this carefully, let me go back to my picture up here for a second. I want you to notice something. I'm going to draw this in another color, say green. If you look at this standing wave pattern that I've drawn, we can pick out, in fact, it's already kind of highlighted in red, but I'm going to go over it in green so you can see what I'm talking about. This is one loop, but this is a full wavelength, right? A crest and a trough. So this distance right here is 1 lambda. 1 lambda, right? Wavelength. You'll notice that a lambda has 2 loops in it. There's a loop here and another loop here. So for a standing wave, a loop is always going to be half of a wavelength. The other thing you will notice is that here is a node at the start, because it's a fixed point, let's say, and then an antinode, a node, antinode, node, and you'll notice the distance between nodes and antinodes, if I cut it up, is conveniently cut into 4. So this is 1/4 of a wavelength, whereas a loop, a full loop, is half a wavelength. So going back to our picture here, what would be the wavelength of this blue wave? Well, we can't see the rest of it. But if you were to draw this crest on top, there would be a trough that kind of follows it like this. Right? If I put this in here like this. There's the wave, crest and trough. The problem is that the string is so short that the trough is being reflected backwards instead of continuing forwards. So it's kind of like the bottom line underneath there, sort of. So what this means is that the length of our string, or the size of our loop, is 1/2 of a lambda, or a wavelength. The length of the string, the distance between the two ends, is really 1/2 of the wavelength that is of the wave that is moving back and forth along the string. And that's a very important thing for us to think about. We give that a name, this simple pattern. It actually has two names. In physics, we call it the first harmonic. But it has an older name that was sort of more of a musical term. Remember that music and physics kind of evolved separately in their own right. And people came up with names for things that, without consulting each other, sort of. In the musical world, this is often referred to as the fundamental. And we'll see why a little bit later. Fundamental, which means the basic one, the most basic, right? Now, this is not the only pattern that you could get, and that's the cool thing about standing waves. So I'm going to draw a line here, and we're going to look at another possible pattern. If I took the very same string and I vibrated it, so let me draw my length of string without changing that, L. Let me put my two little nodes in there, and two little endpoints here and here. And remember, they're both fixed, so they have to be nodes. They have to be places that are not vibrating. It's possible to get a vibration that looks sort of something like this, where I vibrate up and then I vibrate down. This wave could also reflect back off of the end to produce this standing wave pattern, two loops. So we saw that if a wave is if a wave, lambda, is 1/2 the length, double the length, I guess it would be, if the lambda is double the length of the string, or if the length is 1/2 lambda, we'll get the first simplest fundamental vibration. But it's also possible to get this one. It has two loops, and it has a pattern of node, antinode, node, antinode, node. But now something has changed in our relationship. The length of the string is no longer a half a wavelength. There I can see that we're squeezing an entire wavelength into the string. So this is equal to a lambda, not a half a lambda anymore. This would be called, if we continue our little chart, the second harmonic, or the second possible standing wave pattern. In the music world, they call this the first overtone. You can see why we don't like the musical version very well, because the second pattern is called the first overtone. That's kind of confusing. And in the physics world, we call the first pattern the first, the second pattern the second, so we avoid that confusion. But both terms are still widely used. Let's continue this pattern maybe 2 more times to see where this is going to finally end up. Because maybe already you've noticed that because it's a pattern, we can express the pattern mathematically for all possible cases. Let's take the same length of string again. Okay, move that over a little bit, there, just so you can see it visually. That means I have a node at this end and a node at this end of my string. So here they are. So I can basically squeeze in this time this pattern. And when it reflects back, it will produce a standing wave pattern that will look like this. And you'll notice that I have a node, an antinode, a node, an antinode, node, antinode, node. An even more complex vibration. You may also be noticing there's a pattern with a number of loops. In the first harmonic, we have one loop. Right? One loop. But in the second harmonic, there are 2 loops. Now in the third harmonic, which is what this is going to be called, so we may as well write that in, there are 3 loops. This would be called the second overtone in the musical world. 3 loops. Now let's look at the wavelength. Well, I'm going to put in red here. Here is one wave, one lambda. And it looks like it's even smaller. You'll notice that the lambdas are getting smaller each time. The first time it was so big that it actually went past the length of my string. here in the second example, it's equal to the length of the string, but now it's not. Now it is equal to a 1 lambda, but then I would have to put in here another half a lambda to get to the full length of the string. So that's like saying that the length of the string from here to here is equal to 1 lambda plus another half a lambda, or 1.5 lambdas, or 3 halves. Same thing, 3 halves lambdas. All right, one more pattern, just for kicks. And this will be the last picture we draw, and then we'll be able to use a mathematical relationship that will give us all the possible pictures. What's neat about this is maybe you're starting to wonder, can all of these vibrations be happening in that string at the same time? And the answer is yes, they can, which is what makes music so beautiful to the human ear, as we'll see. So here's our last example. Here's a length of string, L. We haven't changed the length. We know we have a fixed end on each end, so we must have a node and a node. So here's my string, here's my ends. Let's see what would happen if I had a different pattern. It's also possible to start with an N and end with an N, a node. If I do this, and this way would then reflect back on itself to produce this standing wave pattern, which now has 4 loops. This would be called the 4th harmonic. 4th harmonic. Or the 3rd overtone. If we look at the relationship of L and lambda, the wavelength, here's 1 lambda. Well, guess what? In order to get the full length of the string, I need 2 of those lambdas, which means the length of this string is equal to 2 lambdas. All right, let's look at these relationships we've written down. Here, these ones, this one, and this next two, right here, right here. For convenience, I'll write them again underneath so we can focus on them all at once. For the first harmonic, first harm, we had the length of the string would be equal to 1/2 of lambda. For the second harmonic, we had the length of the vibrating string or medium would be equal to lambda. For the third harmonic, we had that the length of the string was 3/2 lambda. And for the fourth harmonic, we had that the length of the string was equal to 2 lambdas. To see the pattern more effectively, I'm going to write the 1 lambda as 2/2, 2/2 of a lambda. It's the same thing, 2/2 is 1. And over here where I have 2 lambdas, I'm going to erase that and write the 2 as 4/2. It's the same thing. Still 2, I just changed the way it looks. Now look at what's happening. The length of the string is changing in a pattern. Here it's 1/2 lambda, 2/2 lambda, 3/2 lambda, 4/2 lambda. So you can guess that if we did the fifth harmonic, guess what we would probably get? 5/2 lambda. And this pattern would go on forever, virtually. So in a particular vibrating medium, you can produce standing waves in each of these patterns. The simplest first harmonic, all the way up to the nth harmonic. We use the word n to describe the ultimate one. So for, as a summary, a medium, a vibrating medium, fixed at both ends. That's important because it's going to be different when we change that up. Fixed at both ends. There's a relationship between the length of the string and what we would say is it would be n/2 lambda, where n is the harmonic number. And it's an integer. It's always 1, 2, 3, 4, 5. So for the first harmonic, you put a 1 in there and you would get 1/2 lambda. For the second harmonic, you put a 2 to the end and you would get 2/2 lambda, or just 1 lambda, and so on. So this little expression describes them all. So now we can figure out the relationship between the length of the string and the lambda for any harmonic. So let's see what we can do with this. Let's do a couple of examples. Let's say we have an example. A string is 2 meters long. Find the wavelength for the 8th harmonic. So that would be the 8th pattern that could form as a standing wave. And remember, standing waves can only be these certain patterns. So length would equal n over 2 lambda. If the length of the string is 2 meters long and we want the 8th harmonic, we plug it in like this. And you can see we multiply both sides by 2, so 4 equals 8 lambda. And then if we divide both sides by 8, we would get that the lambda is 4 over 8, or 0.5 meters. Is the wavelength. And that's pretty cool. Later, we'll learn that we can also use this information to tell us more about the frequency of the wave as well. But for now, we have to just kind of stick with the wavelength, because in order to get the frequency, we need to use our little expression V equals F lambda, our universal wave equation. And we haven't talked about the factors that will affect the speed of the wave in a string like this. And it could be different for different kinds of strings and different conditions. Okay? But in a situation where the speed is not changing, two identical strings under identical conditions, then this would be the wavelength for the 8th harmonic. Okay, great. Now, the problem we have next is what happens if we have a different situation? What happens if we have open at both ends? So let's look at example 2. Open at both ends. How will this change? Well, if you're open at both ends, that means that your ends are free to vibrate. So the ends of your string must be antinodes. They can't be nodes. And the simplest pattern in your string from end to end would be a node in the middle. So that would look like this. If my string has a node in the middle and I have an antinode, whoops, I did that a little bit poorly. Fit a node there, it's an antinode, so it would look like this. And when it bounced back on itself, it would look like this. Right? So what's happening here, let me draw something on the side just for a second. Here is the wave, right? And here is the patterns we were seeing before. This pattern looks weird. It's because we're only looking at this section of the pattern. So we're getting that little X-y shape, because instead of starting here where the nodes were, we're starting with it and ending where the antinodes are. But let's think about this for a minute. How much of this wave is showing up here? Well, let's divide the wave into quarters. Remember, we said it's a quarter wavelength between, if this is a node, this is an antinode, node, antinode, node. Well, how much is this part? It's 2 out of the 4 quarters. It's still a half a wavelength. So having it open at both ends means we get a slightly different view, but it's the same vibration. Instead of starting with a node and ending with a node, so instead of node, antinode, node, we're getting antinode, node, antinode. It's the exact opposite, but the length of this section of the wave, which I've shown here, is still a half a wavelength. And just to double check, let's just do the second possible scenario to see. So here's the length of my string. The second possible scenario would be starting with an antinode. Here we go here. And I have to end with an antinode. Well, in that case, I could have this pattern. Oops. A little clearer. This pattern. And it would reflect back on itself to produce this pattern. Well, how much of a wave is that? It's difficult, but it's easier if you draw the full loops. What I have is this much inside my string. How much is that? Well, remember, if this is an antinode, and this is a node, and this is an antinode, and this is a node, and this is an antinode, because that is the pattern that would work here, antinode, node, antinode, node, antinode. There's a quarter wavelength between each one. So 1 quarter, 2 quarters, 3 quarters, 4 quarters. It's still a length of 1 wavelength. The length is still 1 lambda. So it's looking like the pattern is going to be the same if I have open at both ends or closed at both ends. Which means now I can go back up to my little formula that I wrote here, and I'm going to add in here for a medium fixed at both ends or free at both ends. I can save myself a lot of time. This equation produces the appropriate relationship. Excellent. Now there's one more possibility. And I know this is kind of a lengthy video, but we may as well get it all done at once. What happens if you are open at one end and closed at the other? So the third example would be open. Well, you know what? Just because the pictures are easier for me to draw, I'm going to start with closed. It would be the same. It doesn't matter. Closed at one end, open at the other. Or fixed and free. Remember, those words can be used interchangeably. Well, let's think about that. If I'm closed at, here's my string, L. If I'm closed at the start, I need a node here. But open at the end means you have an antinode at the end of the string. Well, the simplest situation is a vibration that looks like this, and it would bounce back on itself. How much of a wave is that? Well, I could continue this way and finish it up like this, and you can see what I'm getting here. It looks like it's half of a loop, or a half of a half, or a quarter of a wavelength. So let me erase that. Okay. In fact, if I draw a picture for you of the standard pattern that we're used to seeing, let's do this one. Because this one has a full wavelength in it. There's a full lambda. I have this much of it in my picture. Right here. And that's the distance between the node and the antinode. It's 1/4 lambda. So in this case, in this simple case, we don't get L equals a half lambda. We get L equals 1/4 lambda. All right, let's try the second case. What's the second possible situation we could get? Let's try the same length of string, open and so closed at the start, and an antinode at the end because it's free and open. Well, the next possible situation I could get would be something that kind of looks like this. I need an antinode at the end. So this would bounce back on itself. It looks something like that. So going back to my picture, to see how much of a wave that is, here's 1 lambda, 2 loops, which show us a full wavelength. How much is my picture? It's from here to here. Well, that's 3 of my quarters. Here's the divisions into 4, right? A node, antinode, node, antinode, node. My picture is this much, and so the simplest situation would be node, antinode, node, antinode, Anna, and that is L equals 3/4 of a wavelength. Because remember, it's a quarter distance. There's a quarter in here, quarter in here, quarter in there. All right, let's do a couple more, see if we can see an emerging pattern. Let's do the next one. And I neglected to write here, I'm kind of shortcutting, but would be called the first harmonic. Okay, we can actually eliminate this picture because this was just there to kind of show you. This is called the first harmonic, so let me put that over here. First harmonic, or the fundamental. Those numbers. This would be the second harmonic, or the first overtone. But of course, it's for a different situation. So now we're going to do the third harmonic, or the second overtone. And we're going to see what that would be. So let's take the length of our string, and let's try to vibrate it. We have to have a node at the start, because that's fixed, and the other end has to be an A. So it's possible then that we could get this kind of picture. A node, antinode. Let's look at this one. This pattern is node, antinode, node, antinode. There's the nana from before, and then we could add a node, but we can't stop there because the end has to be open and free, so we need one more antinode in order for it to work. How much of a wave is this? Well, you can kind of see where we're going. Let's draw 2 waves in here. Here's a pattern that has 1 lambda right there, right? How much of it do I have? I'm going from here to here. That's the picture that I have, which means I have a lambda plus 1 little more quarter of a lambda. So it's 1 1/4 lambdas, right? 1 1/4 is the same as 5/4. So I have 5/4 lambda. I think that's enough to see the pattern. The first one is 1/4, the next one is 3/4, and the next one is 5/4. So you can predict that I'll bet what do you think the next one would be? 1, 3, 5, 7/4 lambda. So now we have a pattern where we're not going up by halves, we're going sort of by quarters, but we're skipping 1. We're going by odd numbered quarters. So we need a relationship that will describe that. Well, here's how you do it. This cute little relationship here, 2n minus 1, will always give you an odd number. Let's see what happens if I put the first harmonic number, n is the harmonic number. If I put the first harmonic number in there, I would get the answer of, whoops, 2n, which is 2 times 1, which is 1, and then take away 1 is 1. Right? So 2n minus 1 gives me an odd number 1. If I put a 2 in there, the next n number, remember the n's go up by integers, 1, 2, 3, 4, 5, 6, 7, I get 4 minus 1, which is 3. So this is my odd number generator equation. I put another 3 in there for the next one, and I get 5, and so on. So I need odd numbers on the top of my fraction, so that's where I'm going to put this little equation to generate my odd numbers on top. But on the bottom, I need fractions that are quarters, so I need to put that on top of the 4, and then multiply that by lambda. Again, where n is the harmonic number, and it's an integer starting at 1. So if I wanted to figure out the wavelength, here's my example. What is the wavelength of the 7th harmonic in a 3-meter string, and I would have to specify open at only one end, which reminds me that in the first example we did, I'm going to go back for a second, bear with me, I know it's a long way back. It was kind of intuitive, but I hope you realize that the example we did, when we wrote the question down, was specific to something that was closed at both ends, right? So let's just jump up here and make sure we make a note of that. When you study this later, you might forget that subtle detail. The question, in other words, needs to tell you in some way whether or not, oh, I think I missed it. The question needs to tell you whether the ends are both open, both closed, or one open, one closed. And in the example that we did, we just assumed that that was the case because it came right after we were studying that. All right, I went way past it. I think it's coming up right here. Okay, a string is 2 meters long. Find the wavelength for the 8th harmonic. We should add in here, the question would have told you closed at both ends. Just in case you missed that. Because you need to know, right? Because it's a different formula, as we see, for one end open. And of course, this could also work for open at both ends. And then the formula we have just discovered now will work for closed at one end, open at the other. And of course, it doesn't matter whether it's closed first and opened at the other end, or opened and then closed, because it's just going to be all the same stuff backwards, and it'll all still work out. So open at only one end, it doesn't matter which end is open. We can say that the length of string is equal to 2n minus 1, which is my odd number of quarters, times lambda. And we can work this out by saying, okay, if the string is 3 meters long, and I want the 7th harmonic, I put a 7 in here for the n, and I get this. And so 2 times 7 is 14, take away 1 is 13. So 3 equals 13 quarters lambda. Multiply both sides by 12. 12, or sorry, by 4. 3 times 4 is 12, equals 13 lambda. Divide 12 over 13 equals meters, equals lambda. That would be meters. Remember, wavelengths are distances. And you could, if you wanted to, punch that into your calculator, but it's just going to be somewhere around 0.9-ish or something of a meter. I think it's 0.92-ish. That's the wavelength of that particular 7th pattern. All right? So that's basically it. We have, to summarize, we have, oh good, we're at the end of our growth here. We have open or closed, both ends, the relationship between the length of the vibrating medium and the wavelength of standing wave patterns that you can get is n over 2 lambda. And for open at one end only, we have L equals the length of the medium, 2n minus 1 over 4 times lambda. All right? And so what this means is you take a string and you can produce any one of these patterns, or many of these patterns at once. And as we'll see soon when we talk about musical instruments, the number of standing wave patterns that you produce and the sensitivity of your ear to each of these patterns is what produces the unique sounds of all the musical instruments, including our own voices and virtually any vibrating object. So that is the mathematical approach to standing waves. Lots to look at, lots to get your head around.